Okay, I guess we can start. Can you hear me? Yeah. Good morning, everyone, and thanks for being here. My name is Ludovico Boratto, and when I presented this tutorial proposal, I was working at the University of Cagliari in Italy, but I recently moved to Barcelona, and I'm working from the EURECAT, which is a technological center. So, in this tutorial, we will tackle the problem of producing recommendations for groups of users. This talk is divided into 5 parts, in which we will briefly introduce the problem of producing recommendations to groups. Then we will analyze in detail the tasks that a group recommender system performs, and we will also consider how the approaches in the literature deal with these tasks. And next, we will consider the evaluation methods, which, as most of you know, is a challenging problem in recommender systems in general, so also for group recommender systems. And we will continue with some emerging aspects and techniques that have been recently applied to group recommender systems. And then we will have a brief summary and concluding remarks. So, as most of you know, in general, recommender systems work with individual users. So, when we have a group of users, which, for example, might ask themselves, where shall we dine? The system has to deal with the fact that each individual user has her own preferences. For example, you might have someone who's on a diet, someone who is a vegetarian, and someone who loves Asian food. What a group recommender system in general has to do is to combine the individual preferences and to predict what the group as a whole might like. So in this example, a good recommendation would be a light vegetarian restaurant. Here we provided an example in which we have a group of people that wants to dine together, but group recommendation can be naturally adapted to any scenario in which you have a group of users and a decision-making process. You might have friends going to the cinema together, and the system would recommend the movie that they could see, or a group of users planning a trip. So the recommender system might combine the individual preferences to recommend to these users where they could go. Going a bit more formally into the problem statement, we are given a set of individual users, a set of items, and a set of values that are used to express the preferences. Of course, you might have different scales from 1 to 5, or a binary scale in which the users just express whether they like or dislike an item. And then we represent as R the ternary relation that contains the preferences given by the users. When we deal with a group recommender system, we consider the fact that a set of users is split into K groups. And each group usually respects some properties. So all the users in a group receive the same recommendations. In general, all the users belong to a group, so that every user can receive a recommendation. And in general, groups do not intersect. This will avoid that each user would receive multiple recommendation lists. So, given a group and a set of items, the objective of a group recommender system is quite similar to that of a classic recommender system. So it is to identify an item with the highest predicted rating. Of course, since we are dealing with a group of users, a set of challenges arises. So we have to consider the fact that the groups themselves might have a different nature. So you might have more stable groups, or some groups that just formed for a specific aim, or some groups that might even be completely random. Then, should the preferences be collected for each user or for the group as a whole? How should the individual preferences for an item be merged, be combined into a group preference? Should the ratings be predicted for each user or for the group? Who should choose the items to recommend to the group? The system, a member of the group, or maybe a group might have a conversation. How can the recommendation be explained to the group? So, during this tutorial, we will try to provide an answer to these questions by analyzing the different ways in which the systems in the literature deal with these aspects. So we will analyze the different types of groups that a group recommender system usually handles, how preferences can be acquired, how the individual preferences can be modeled into group preferences, how the ratings can be predicted, and how can we help the members to achieve a consensus, and how to explain the recommendations to the group. So let's start with the first aspect, the types of group. In this paper from 2011, we provided a classification of the different types of groups that a group recommender system usually handles. And this classification was also adopted by Carvalho et al. in the DAB paper in 2013. So usually, a group recommender system can work with an established group who shares same interest, usually for a long time. For example, the members of a forum of a specific artist. Then you might have an occasional groups who might have a specific aim in a given moment in time. For example, a group of people that is participating to an organized travel. And then you might have a random group of people who do not have anything in common. For example, suppose that you have to decide which background music you should play in this room. No, maybe in this room is not correct because we are linked by a given interest, but in a mall, in a given place. So, the systems that work with established groups usually are characterized by specific domains. For example, there's Booleans, which is one of the oldest and classic group recommender systems, one of the most famous one, which considers the fact that people usually goes to the cinema with the same friends. Or there's this group recommender for online communities, which tries to provide recommendation by considering the fact that the users belong to a given community, and the people share interest and share information. When considering occasional groups, you might have domains like people, for example, going to the gym together. So if you have to provide music recommendation to people working out in a gym in a given time, you have to consider that there are not specific interests that link these users. Then there's Intrigue that suggests tourist attraction to groups of users traveling together. And the system can also work with subgroups to consider the fact that there might be some categories that have special needs. For example, children or disabled people. Or another approach, which is more recent, but also quite good and received quite a lot of attention in the literature, is this paper by Liu et al. From 2011, which defined event-based social networks, in which we have communities of people who attend social events, and the system considers both the fact that the users have online and offline interactions. When considering random groups in the literature, we have some good examples. For example, we have Let's Browse, which is a system that assists group of users in a collaborative web browsing experience. So the system detects the presence of the users in front of the screen through an active badge and tries to merge the preferences of the individual users to help them browse the web together. Then we have Gain, which is a system that recommends news to a group of users that are in a public space in a specific time. Or Fit, which is a family interactive TV system, which looks at the probability of each family member to watch TV in that time slot, so it tries to automatically derive who there might be watching TV and tries to provide predictions to the group by trying to deriving also who there might be in front of TV. Then the last two systems we will see that consider random groups are Flytrap and Ucola, which are two systems that select music to be played in a public room. Flytrap considers the preferences of the users present in the room at the moment in which the song gets selected, while Ucola allows artists to upload their MP3s and allows the people in the room to express their vote. Here you see a screenshot of, and you see that the users have an interface in which they can express vote, and so that the system can decide what music to play. Here are just some initial examples, and I hope you already noticed that the fact that dealing with different kinds of groups already leads to different ways in which the systems manages these groups. But throughout the tutorial, we will see that these characteristics of the group also have an influence on the subsequent tasks. Let's consider the fact that, of course, in order to provide recommendation, preferences have to be acquired. A system can acquire explicit or implicit preferences, and these preferences can be collected by considering that a user is a part of a group, so the system might allow to gather also group preferences, or it simply considers individual preferences as a classic recommender system would do. Let's consider some systems that allow users to express group preferences. CATS is a group recommender system in which the members can interact and express preferences around a shared device which is called Diamond Touch Tabletop. As you can see, each user has what is called an individual space in which she can express the individual preferences. These individual preferences are then shown into a group space, which also show which places the individual users considered. Then, when considering the group preferences, the system considers for each destination the preferences expressed by the individual users. Here you can see that these two users expressed a positive vote, while there's a question mark that indicates a missing preference. And then another characteristic that is interesting is the fact that the users can provide critiques. So they can have an influence on the final recommendation. Another example we're going to see is a travel decision forum in which each member can view and also copy the preferences of the other users. So here on top you can see that you have a section that is called My Group, and for each member of the group you have an option that allows both to show or copy the preferences of the other members in the group. This would speed up the preference acquisition process. And so you see that for different types of facilities, for different types of characteristics, the users can, again, view the preferences expressed by the others. So here we see that for health facilities, we have for each user how important it is, this feature, when considering a travel. Then we can see the ratings that each type of location that offers this type of feature has received. And so the system can help in some way the interaction between the users. We will see also that the system supports the interaction between the users in other ways. We will see this aspect later. In this paper from 2010, the system allows both individual and groups to express preferences. So, for example, it considers the fact that when watching a movie, the individual preferences and the group preferences might be different. So somehow the group preferences are adapted because of the fact that the user is part of a group. And in this paper by Chen et al. From 2008, it is assumed that both individual and subgroups express preferences. When considering individual preferences, I decided to avoid classic, ratings that can be also found in classic recommender systems, in the individual recommender systems. And I try to focus on some specific cases in which the system considers individual preferences in a group recommender system. Here we can see that co-fill is a system that allows to express through colors and emotion, through colors the emotion that a song gave to the users. Then these emotions are used in order to decide which music should be played for a group. So here you can see that each user has a set of emotions he can express, and he can also express the intensity. So if the song makes him feel agitated or excited or happy or whatever. Another particular example of individual preferences is music effects, which lets users also express negative ratings. So the users can express preferences in a range from -2 to 2. Or adaptive radio, which makes even a stronger assumption and considers only negative preferences to avoid playing music that might not be liked by someone. So the system says, okay, if this artist, if this album is not liked by one member, I will avoid playing this music for this group. Then there's this interesting theoretical study which has been performed on the preference acquisition domain, which was published last year. And the authors in this paper consider the fact that Usually recommended systems work with partial information, and moreover, some users cheat. So there's some kind of misbehavior that the system should consider. So the authors ask themselves, what is the minimum number of ratings that a product needs so that one can make a reliable evaluation of its quality? The authors developed theoretical models which were also validated on the Netflix and Amazon datasets in the group recommendation context. So if you represent as and first the minimum number of ratings that are needed in order to tolerate the misbehaving user, and we analyze the probability of this minimum number of ratings to be higher than n in order to produce reliable recommendation, we can see that the two data sets produce completely different results. Here you can see that each line in the graph represents a different way to combine the ratings, and we will analyze more in detail these aggregation strategies. But here you can see that, for example, if you aggregate individual preferences with an average score, the probability that a group recommended system, in order to produce reliable recommendation, needs more than 150 ratings is very, very low. So let's move on and let's see how the individual user models should be combined in order to form a group model that contains the preferences of the group. What we're going to analyze is our group modeling strategies that combine, as I said, individual preferences in order to form a group preference for the item. There's a study on the topic which was performed by Pizzutilo et al. In 2005, which says, here I quoted a sentence that says that there is no strategy useful in every context independently from the environment. So what the author says is that the group modeling strategy should be selected and evaluated in the context in which the group is modeled. So there is not like such a perfect strategy or a strategy that outperforms the others in all the contexts. So the topic has been mainly studied by Judith Mastoff for more than 10 years, and the most recent work that involves all these strategies is actually the chapter that was published in group recommendation handbook that considers all the 11 strategies. So let's see how these strategies work and how they've been employed in the literature. In order to present the group modeling strategy, we will use an example in which we will consider 3 users, 10 items, and each element of the table represents a ratings from 1 to 10. So here you can see that user U1 gave a rating 8 to item I1. The first strategy, which is also the most simple one, is the additive utilitarian one, which simply adds the individual ratings for each item, and it is also known as average strategy. So, because the order ranking for the items for a group is the same. So, as you can see, what this strategy simply does is to sum the individual ratings in order to form a group rating. This strategy has been used a lot in the literature, and as an example we can see Pocket Restaurant Finder, which recommends a restaurant to a group of people, and in order to combine the preferences, the system creates an average of the individual preferences of the group for different types of feature, for example, the location, the cost, etc. In this very famous paper from 2009, probably one of the most famous papers in a group recommender system, the modeling strategies create an average of the individual preferences, but also take into account that the members of the group might have a disagreement. In this paper by De Pessemir and al. In 2013, the author illustrates that modeling the individual preferences with an average is actually the best way in which a group can be modeled in different contexts. The next strategy, which is quite similar to the previous one, and also the names are very similar, is called multiplicative utilitarian strategies. So, this strategy, instead of summing the individual ratings, multiplicates them. So, as you can see, that two strategies generate completely different results. Here you see that if we previously summed the individual ratings for items I2 and I3, we obtained a score of 21 for both the items, right? While if we multiplicate them, the results, the group rating, are very different. In a paper from 2011, Mastov showed that this strategy works best when selecting a sequence of television items to suit a group of viewers. And for those of you who attended the user in loop session 2 days ago, you saw that in a paper that was presented here at RecSys, they showed that this strategy is actually the most accurate also in real-world scenarios. The third strategy we're going to consider is called Borda Count, and in this strategy, each item gets a number of points according to the position in the list of each user. So, the least favorite item for each user gets 0 points. The next one receives 1 point more, and if two items get the same number of ratings, points are distributed. Let's see how this strategy works with a practical example. Let's consider user U2. As you can see, for these users, items 8 and 9 are his least favorites because they received both a score of 4. So they share the lowest point, 0 and 1, and both items get a 0.5 score. So the individual ratings expressed by the users are substituted with these scores, and the individual scores for an item are added, and the items are ranked by score. This strategy is actually the most accurate when selecting a sequence of television items for a group of users. And in a very recent approach, which was published last year and is called Travel with Friends, this strategy is used to rank the top 5 travel destinations that are recommended to a group. The fourth strategy is called Copeland Rule, and it is a form of majority voting. And the strategy sorts the items according to a so-called Copeland index, which represents the number of times in which an alternative beats the other minus the number of times it loses. Let's see how it works. It's very easy, but if you don't follow me, feel free to interrupt me. Let's consider items I1 and I2. We can say that item I2 beats item I1 since it is preferred by both user 1 and user 2. Okay? So what we do is we generate a table in which we have the items both in the rows and in the columns, and we represent with a plus the fact that item I2 beats item I1, and with a minus the fact that item I1 is beaten by item I2. What we do next is to basically sum this score, and of course we can obtain a ranking of the items for the group. So in this case, you can see that item I6 would be preferred by the group by a large extent, according to this strategy. An approach that was published in 2010 proved that a form of majority voting is actually the most successful when a system has to perform a requirement negotiation. The plurality voting strategy allows each user to vote for her favorite option. If the system has to select more than one alternative, the items that received the highest number of votes are selected. So, in our example, if user U1 has to choose her favorite option, she would choose item 2 or 4 or 7, right? Because they received the highest score. So what we do is to represent the first choice of each user, and then the system would make a choice based on the individual preferences. So in our case, the first item that would get recommended to the group would be either I2, because it received 2 votes, or I6, because it also received 2 votes. As I said earlier, in case more than one decision has to be made, the strategy is simply repeated. So the second choice of user I1, of course, would be either I4 or I7, because I2 was already chosen. This strategy is not widely used in the literature, but there's this paper by Seno et al. In 2007 that tests this strategy in the TV domain. The next strategy we're going to analyze is called approval voting, and assigns a point to all the items the users like. Suppose that each user votes for all the items that got a score higher than 5. So these ratings that you see highlighted would not be considered, because they would have a score that is too low, and to all the other items we assign a point. What the strategy does is to sum the individual points in order to rank the items to recommend to the group. This strategy has been used in different contexts in the literature. You can see that to recommend the pages to suggest to a group, the approach that we saw earlier, Let's Browse, which helps users in a collaborative web browsing experience, evaluates if the page that is currently considered by the system matches with the user profile above a certain threshold, and recommends the one with the highest score. And in this paper by Borda et al. In 2011, the strategy has proven to be successful in contexts in which the similarity between the users in the group is high. The next strategy we're going to see is actually very simple but very interesting at the same time, and it is called list misery, which assigns as a group rating the lowest rating that is expressed for an item by any of the members of the group. So the strategy is usually adopted to model small groups to make sure that every member is satisfied. Let's see this example, which is quite interesting in my opinion. We said that the rating that would be assigned to the group is the lowest rating given by any of the members. So in this case, the group rating would be 8. And I hope you can see that if the group gets recommended an item with such a high predicted rating, it means that surely everyone would be satisfied with this choice, right? The most famous paper that uses this strategy is Polylens, which, as I said earlier, produces movie recommendations that satisfy the small groups that the system handles. Usually, the system works with groups that are composed by 2 or 3 people. Then there's this very recent approach, which is called the group link, which we're going to see also later, which recommends a set of activities to a group of users, and each user has to be recommended a minimum number of activities she enjoys. Most pleasure is actually the opposite strategies of list miseries. So it assigns the highest rating expressed for an item by any of the members of the group. So here you can see that in this case, the group would get recommended this item with a score of 10. And this strategy has not been widely used in the literature, but it was used in this paper in 2011 to face the cold start problem. Average without misery is a strategy that creates an average of the individual preferences, but it does not consider an item if it received a score under a given threshold by at least one of the users. In this example, we are going to consider all the ratings under 4, and you can see that since this item was not liked by a member of the group score does not appear in the group model. One of the approaches that we talked about earlier, the one that decides which music should be played in a gym, sums the individual ratings expressed by the users, but it does not consider the items if it received a score which is under a minimum degree of satisfaction. The next strategy is called fairness, and as the name says, it supposes that a user can get recommended something that she does not like, as long as she also gets recommended something she likes. What this strategy basically does is, in rounds, decide each user what is her favorite items, and if 2 items have the same rating, the choice is based on the other users. So, in our example, let's suppose that U1 is allowed to choose first, and she would choose item I4 because it is the one that is most preferred by the others with respect to I2 and I7. Then U2 would be allowed to make a choice, and she would choose I6, again, because it is the one with the highest average. Then I3 would choose I10, because I6 was already chosen. And U3 would be allowed to choose again, because he was the last one who made a choice. Then again, I won't go into much details, but as you can see, here you obtain a sequence of items that would get recommended to the group, and the strategy allows each user to make a choice in turn. The strategy was adopted in the music recommendation domain in this paper by Christensen and Schiaffino in 2011. The last strategy we're going to see is actually quite interesting, and it is called most respected person or dictatorship. In this strategy, it is assumed that there's a person in the group that acts as a leader. So it is assumed that the strategy considers the preferences of a most respected person, and it uses the preferences of the others just in case one item received the same evaluation. So in our example, let's suppose that U1 is the most respected person, so she would make a choice. As you can see, this strategy has been adopted in various contexts in the literature. We have intrigue that, as I said earlier, advantages subsets of users with particular needs. Then we have gain, in which the authors show in the study that when people interact, just a user or a small portion of the group influences the choice of the others. Then we have this paper from 2011 by Jung, which considers long-tail users, which are users that are considered as experts on certain attributes, and their ratings are considered to provide recommendation to the non-expert user groups, which are called shorted groups. Then the last paper we're going to see is a paper from 2011 by Berkowski and Fein, which considers that when a family is preparing a recipe, the person that is actually preparing, is actually cooking, has a higher weight with respect to both, for example, a partner or her children. So now we saw the main strategies with which we can move from the individual user models to the group model, so to a model in which the preferences of the group as a whole are represented. Let's see how we can actually implement the rating prediction process, which is the core of a recommender system. In this survey from 2007 by Jameson and Smith, the authors identified that in a group recommender system, ratings can be predicted using one of these strategies. The first is to consider the group model we just saw and build the predictions for the group using the model. The second approach merges the recommendation that are built for the user in the group, and the third strategy aggregates all the predictions built for the users in a group. So as you can see, strategies 2 and 3 are very similar. The difference is on the number of items that are considered by the rating prediction task. In this case, it is just the recommendation, so we might also call them the top n items that are predicted for the group. And in this case, all the ratings that are getting predicted are considered in the group recommendation process. So let's see how each of these strategies work. The strategy that considers the group models builds a group model with one of the strategies we saw earlier and combines the individual preferences. Then the rating for the items that do not have a score in the group model are predicted. So we first construct a model for a group G, which contains its preferences, and for each item I that was not evaluated by the group, we use the model to predict a rating for the group. Music effects decide the genre of music to play by randomly selecting one of the top n stations that are available in the group model that was built by summing the individual preferences. The choice to consider random station was made to avoid playing the same genre of music every day. Then we have again Intrigue, which models the preferences of subgroups of people with homogeneous preferences. And as I said earlier, it gives a different importance to particular categories of people, for example, disabled people. Other approaches that work with groups, with group models, are this approach that was presented in 2010, which showed that when recommending recipes to a family, a group model that combines the individual preferences should be used to make the predictions. Or when recommending TV programs to a group, TV4M builds a model with the family members who logged in, so who are in front of the TV, and it builds the prediction using this model. Moving to the second family of approaches, the one that merges individual recommendation, it presents to a group a set of items which is the merging of the items with the highest predicted ratings for each user in the group. So, what the approach basically does is to consider each user in the group, to build individual prediction, and then the approach selects a set of candidates for each user who have the highest predicted ratings, and it models the preferences of each group by producing the union of the candidates that have been built for each user. This approach has not been widely used in the literature, but Polynese, which, if you remember, is the system that recommends movies to watch for a small group of users, selects the item with the highest predicted ratings for each user, and, as I said earlier, it employs a list misery strategies to recommend the one with the lowest rating. Moving to the last family of approaches, we have the one that merges individual predictions. So, the approach is very similar. Again, we build individual predictions for each user, and then instead of considering just the top n items with the highest predicted ratings, we calculate an aggregate ratings for considering all the predictions that have been built for each user. Pocket Restaurant Finder predicts a rating for each user and in each restaurant and combines them with an average, as I said earlier. Instead, the Travel Decision Forum builds prediction for each user, and as you remember from earlier, users also can copy and view the preferences of the other users, and then it predicts a group score by considering the median of the individual predictions. Eturism, which is a group recommender system that was developed and presented in 2009, builds three types of predictions for each user, which are demographic, content, and like-based, and aggregates them and selects group recommendation from each list. So, now that we analyzed how to model the group preferences, and now that we can build predictions for a group, we can see what we should do with these predictions. So how can we help the members of the group to achieve a consensus. A group recommender system to help the users find an agreement on what should be recommended to them uses these three strategies. The first is to suggest the items with the highest predicted ratings without consulting the group, as like a classic individual recommender system would do. In the second approach, a member of the group is responsible for the final decision, or the users in the group have a conversation in order to achieve a consensus. I skipped the first approach because it is quite classic and it does not have anything interesting to present. And I'll move on to the second approach, in which a member is responsible for the final decision. An interesting example, in my opinion, is Travel Decision Forum, which allows the tourist guide to make the final decision. Here, as you can see, the tourist guide is called the mediator. And the system actually helps the mediator getting a decision by selecting the mechanism to generate the proposal. So he can generate them with an average, and the system highlights that this approach can be manipulable, or with a median, which is non-manipulable and transparent, and or with a random choice, which is also non-manipulable and transparent, or automatically generated and non-manipulable. And the mediator can also select if he wants to prefer utility-based recommendation or recommendation that focus more on equity. Then this other approach that was developed in 2006, in which the expert of the group can express an opinion on an alternative, and this expert can use linguistic labels. For example, this recommendation would be perfect. And the system aggregates these linguistic labels, which are introduced to facilitate the decision process to the expert, and makes a final decision. Moving to the conversation between the users, so from the case in which we have just one user that is responsible for the final decision, to the fact that the users talk among themselves, Travel Decision Forum also allows users to have a conversation. If the users are not in the same room, animated characters, which represent agents, represent the likely response of the absent. So, for example, here you have two users which cannot have like a proper discussion, and based on the preferences that the users can express, you have these animated characters, these agents, that have a conversation among themselves. So, for example, you have the user on the left, which says, regarding beauty farm and importance, the ratings are just too high for me. And then the proposal for massage is much too low for me, and what's more, the proposal for fitness is much too high. So in that sense, as you can see, the agents find in the end that they have to look for another proposal, because thanks to this discussion, the users cannot find an agreement. The last task we're going to see is how to explain the recommendations to a group. Of course, the problem of explaining recommendation we're also seeing in this conference is quite central at the moment, because it might not be trivial for a user to understand why the items were get recommended to her. So, as you can imagine, having a group of people makes this explanation process even more important. So, some systems also explain why the proposed items have been selected for the group. Polylens, which is the system that recommends movies to watch for a group, presents the group recommendation, which are here in the middle of the table, and also showing the individual ones. So here you have your, and then you have the other members of the group. Remember that in this system, users, the groups are quite small, usually 2 or 3 people. So it is quite easy for the individual users to understand why an item got recommended. Instead, let's browse, which is also from the interface. You can see that it is an approach from 1999. Is a system that shows the keywords that led to the recommendation. So this page might interest Bill, George, and Nicholas because it concerns technology and travel. And here you can see that actually Bill Gates has among his keywords technology and travel, and also George Lucas has these 2 keywords. So while explaining why a page was recommended to a group, the system highlights the keywords. Another interesting approach is to explanation is the one proposed by Intrigue, which gives a long explanation of why a destination was recommended to a group. So let's see this example. You see that the second item that gets recommended to the group with 3 stars is Palazzo Reale. And the system says that for children it is much eye-catching, and for yourself it is eye-catching, and it has a high artistic value. For impaired it is much eye-catching, and it has a high artistic value. So as you can see, the different members of the group and the characteristics of the different members of the group are considered, and an explanation is provided. Moving on to the evaluation methods, the classic, I would say, approach to evaluation in the recommender system is also adopted in group ones. So we have 3 approaches, which are offline methods on existing datasets, user surveys that evaluate the effectiveness of a system by asking users to answer questionnaires, and then we have live systems that work in real-world domains like the social networks. With the offline methods, I won't go into much detail because they employ the classic metrics that have been used, like RMEC or MAE or precision and recall. But one aspect I would like to highlight, I guess it's a key aspect that characterizes group recommender systems, is that no public group recommendation dataset is available in the literature. So in general, of course, you might have the preferences of the individual users, but the partitioning of the users into groups is usually not available. And the vast majority of the approach adds a constraint on existing and published datasets to infer the groups and build the recommendations for them. When working with user surveys, users are asked to compile a questionnaire to evaluate the system, and here I highlight 2 recent papers in which one evaluates the quality of the recommendation by asking the users explicitly how satisfied they were, or there's this approach by Zapata et al. From 2015 that asks the user to evaluate the usability of the system. So as you can see, the authors try to move on also from the classic relative prediction problem and evaluate other aspects. For the live system, I decided to provide this example, which was presented in a very recent paper, and I think it's also quite interesting, which is called the group link, and it suggests events to promote group members' face-to-face interaction in no-work settings. So the system identifies and tracks personal preferences by analyzing individual digital traces. So the user basically allows the application to enter in his social media account, in his email, and in the online streaming stories. And an actual live system was developed, and it is actually available online. And as you can see, the mobile application provides the group recommendations to the users. In the last part of the talk, I will focus on emerging aspects and techniques which I believe are characterizing the recent literature. In particular, we will focus on 4 aspects. We will see how the recent advances in recommendation technologies have been applied to group recommendation. We will analyze the temporal aspects, how temporal aspects have been considered in a group recommender system. Then we will consider social recommender systems and group recommendation with automatic detection of the groups. So a scenario in which also the groups are not available and should be detected. Advanced recommendation techniques. As most of you know, in the recent year, to address problems such as sparsity and limited coverage, new recommendation techniques have been developed, and 2 main research directions have been identified. One is the dimensionality reduction 1, in which there is a compact representation of the users and the items in order to characterize them with the most important features, or graph-based techniques which exploit the transitive relations in the data. And these 2 classes of approaches have been recently adopted in group recommendation items too, in group recommendation problems too. The first example of dimensionality reduction in a group recommender system is from a paper by Christensen and Schiaffino in 2013, which employ matrix factorization and social network analysis to evaluate the social influence. So as you can see, the authors start from the social network and evaluate 3 metrics, which are called centrality, the social similarity between the users, and the cohesion among the users measured with the trust. So for each user, these 3 properties are measured. Then the predictions are built with a classic matrix factorization approach, and what the authors do is to modify the ratings that have been generated with the matrix factorization approach with the social features that characterize the users. So we have a modified rating matrix, and then the individual preferences are aggregated with the strategy I previously presented you. Moving to the graph-based technique, that there's this approach that was presented in 2015, which presents a stochastic method. And the authors build a bipartite graph and perform random walk to quantify the influence of the nodes. So as you can see, we have the users, we have the items, and we have the tags that the users have employed to classify these items. The intuition behind this approach is that similar users are close in a random walk, and the items that are most interesting for the users are also easily reachable in a random walk. So basically, they build these matrices, one, for example, for the user and the items, or for the users and the tags, or for the items and the tags. And as I said earlier, they perform these random walks in order to decide what should be recommended to the group as a whole. Then we consider COM, which stands for consensus model, which builds a generative model that incorporates user selection history and personal consideration of content factors. So the authors start from the assumption that users in a group may have different influence. For example, someone may be expert in a topic. So as you can see in this post, we have this user that is a group member that checked in at this steakhouse, so in this venue. And in the post that the user actually does is the user basically tags another user and says, having dinner with my sweet husband, and the username of the other group member. So, as I said earlier, what the authors do is to build a generative model in which basically the authors describe the distribution of the topics for the users, the distribution of the items for the user, and provide recommendations to the group as a whole. Considering the temporal aspects in group recommender systems, between 2014 and 2015, 2 papers emerged that consider this aspect, and time has been actually considered in a very different way. In the first approach by Chen et al., the authors construct a temporal influence function that reduces the interest of a user toward an item as time passes. So it is a form of aging that has been applied to a group recommender system as well. A more complex approach was developed in 2015, in which the authors analyzed the evolution of the affinities between the users over time. And the authors built 2 models. One is a discrete model in which time is discretized over a set of time periods, and the affinities are computed for each subperiod of time. The second model that has been built is actually a continuous one, in which time is represented as an exponential function that positively or negatively affects the affinity over time. Considering social recommender systems, among the papers that have been presented over the last years, I decided to focus on what is actually a real-world Facebook application, which is called Happy Movie, which recommends movies to the group. What the system does is basically to consider user preferences as a classic recommender system would do, but it also considers the social interactions among the users and the personality that they have. So as you can see here, you have a real-world application in which you have 2 members, and the application and the approach was evaluated by 60 users and to evaluate the quality of the recommendations. The last aspect in which I will focus is the research area in which I've been working on over the last few years, in which we consider the fact that sometimes groups might not be available as well. Let's consider an application scenario so that we see why this problem might be interesting. Let's consider recommendation flyers that are sent to the users. Nielsen recently estimated that 1 billion users per year is spent to print 12 million flyers in Italy alone, and that 14.6 billion euros are estimated to be spent by the customer thanks to these flyers. So you can see that behind this market that there's a strong interest. What companies usually do is to send the same flyers to all the users. But of course there would be a problem with targeting. There would be no personalization. But one might think, okay, a company has all the information it needs to provide a different flyer for all the users. But in this case, costs the cost of producing a different recommendation flyer for each user would be too high. Let's suppose that 10 flyers represent a feasible cost for the company. It would be necessary to identify 10 groups of users so that each group would be addressed a flyer with content that might interest its members. As you can see, this application scenario is quite different from the others because we have a group that has to be identified automatically. So we asked ourselves, how should we predict the ratings in this context? So if we should predict them for individual users or for the groups, how we should group the preferences, how we should group the users for recommendation purposes, and how we should generate group models that contains the preferences of the group. Among the studies that I performed, here there's one that basically summarizes most of my findings. And the interesting aspect of this research area is that you should predict ratings for individual users, and then these individual predictions should be included as input in the clustering algorithm. So even the predicted preferences are a valuable source of information in order to detect the groups, which can be detected with a simple clustering algorithm like k-means. And the groups should be modeled to an average of the individual ratings, so the additive utilitarian strategy I previously presented, because it recreates the centroid of the cluster. I will conclude this talk by identifying some that I identified as possible open issues and research challenges in this research area. As we said earlier, there is no public data set available that contains both the group structure and the individual or the group preferences. Regarding the evaluations, there's still a problem of evaluating how effective are the recommendations for the group. We might evaluate through classic metrics how satisfied each user was with the recommendation, but there's still no metric or no way to identify how satisfied is the group as a whole. There might be problems with privacy, especially with explanation. And if you consider the fact that there's the so-called big data problem, so you might have lots of data, the fact that a group recommender system has to perform additional tasks might be a problem when considering the efficiency of the system. And then the last problem I identified is the one of generating novel, diverse, and serendipitous recommendations, because it is a problem in the individual recommender system, in recommender systems that work for individual users. And of course, as you can imagine, having multiple users, finding something that is both novel and diverse for more than one users is even more challenging. Okay, so if you have any questions, I'd be happy to answer. Thank you.
Thank you so much for the talk. It was really amazing. When you mentioned the theoretical studies, you said that some of them identified, or one of them identified misbehavior. and that it should be considered. Can you explain a little bit, because I'm not familiar with those studies, what kind of misbehavior we are talking about?
So suppose that someone assigns fake ratings. For example, you are on booking.com and to disadvantage a structure, you assign a lower rating with respect. You have to consider both the fact that the ratings are usually very sparse and the fact that some of these ratings might be associated to misbehavior. This is an example, for example.
Thanks for the great talk. You mentioned explanations as helping with the group decision. Might there be also explanations hindering the group decision? Like you tell them, we decided this because of member A, but actually the people don't like member A so much, so they decide against it?
Okay. So when providing an explanation, you have to consider the fact that usually the decision has been already made. So, for example, let me go back. As you can see, here you have already the group rating. So a decision has been already made. So an explanation is like something additional that helps the user. What you're referring to is probably, from my vision, would be like a mix between the explanation and the conversation. So maybe when basically the decision process is being made, providing also an explanation. And in that sense, I agree that if one user does not like the other, this might also help the decision-making process and the explanation itself. And yeah.
Thank you.
Thank you for this tutorial. I want to go back to this topic of, let's say, group preferences. You always talk about group preference, but actually group preferences are not existent. So you do not have a group with preference. You always have individuals with preferences. What the groups have is essentially choices. So at the end of a process, a group can make a choice. So what you can compare is, let's say, individual preferences with group choices. And so can you elaborate a bit more? Because this is a fundamental problem with group recommender system. You do not have group preferences, so you cannot even easily evaluate a group recommendation, because you can only check whether a user is happy about a group recommendation, but not a group is happy about a group recommendation.
Okay. When group preferences can be expressed in the sense that, for example, if a man alone was asked to rate a romantic movie, it would probably give to that movie a low rating. The fact that the couple as a whole is watching the movie might create an experience with respect to the item that might make most possible to associate a unique rating of the group, in that case of the couple, for the movie as a whole. In that sense, in my opinion, you can have group ratings which are different from individual ones. But
in this case are not the group ratings, are individual preferences that are changed according to the context. So is again, so a user is, let's say, happy with something because in this context of the group, he's doing something that maybe he could not have choice to do alone. But again, you have only individual preferences, you do not have group preferences.
Yes, what I think the approaches in the literature do is basically to, maybe it is, I agree, somehow a forced approach to ask to the couple to express a unique rating, but somehow they find an agreement between themselves. But I agree that preferences are of course individual, but somehow yeah, they adapt the individual preferences to make group ones.
Another question. What you have shown here, essentially, prototypes that have been produced by researchers. In which area have you already seen some real commercial, let's say, operational group recommender system? Are there? Are maybe not that as clearly detectable, but they are or not?
Okay, from what I know, there are no like commercial group recommender systems because I think I thought a lot about this topic, and the problem is that the recommender systems are usually web-based, and the web experience is usually individual. So I think that having like a commercial product that targets the groups might be useful, for example, to recommend events that might be performed by the group as a whole, but there are no commercial systems also because I guess it is hard to, for privacy reasons, to find what the group structure is and to collect their preferences. So, for example, Facebook might have groups, but you're not allowed to see how users are grouped in the circle of friends of specific users. So, from my experience, these prototypes are the only things that exist, and I think it would be valuable to have a group recommender system, especially for events or things to do, but I guess privacy makes it hard to make them.
Thanks. So first I want to agree with Francisco that preferences are modified by, individual preferences are modified. I'm not sure that there are group preferences. But there's a more subtle issue even in judging the recommended item, because we often ask people what they think of the item itself, but what matters is the experience, right? So it may well be that you see a film with your child and you hate this film, but with your child, the experience of watching it is a joy. And we're not making this distinction properly in group recommender work.
Yeah, I agree on that.
So another observation, whilst there aren't many group recommender systems out there, what there are systems that recommend people to others, often with a view to creating groups, right? So if you think about some of these event recommenders, they tell you that people in your social network are going, and so there is an implicit group formation being, as well as event recommendation going on at the same time. I wonder if you want to comment on the role of that work in this survey that you've presented.
Sorry, can you repeat, please?
My observation was that there are lots of real systems, whilst they're not actually group recommenders, you don't form a group and then try and choose something together. They are jointly recommending an event and some people in your network that you could go to this event with.
Yeah.
And so this is potentially something that could use group recommender ideas. And I wondered if you had anything to say about that on the basis of the survey that you've done.
Yeah, I guess the main difference is that if the group, if the group as a whole is available of the recommendation, because as you told me, it might recommend to individual users both the group and the events, but the group as a whole is probably not aware of what kind of recommendation it is receiving. So I guess this is the main difference. If you have any other questions, or maybe you are interested in collaborating in the conference proceedings, you can find a summary of this tutorial where you have all my contacts, and so I'll be happy to hear from you and maybe, I don't know, discuss ideas, collaborate, and or maybe answer questions or link you to papers that might be interesting for you. Okay? Thanks a lot for being here.